Hello, it's been a very long time not meeting with you guys because I was like very busy during the last month, but now I'm back. And I remember last time we talked a lot about the random variables, like how they're defined and how to check them, like which function is a random variable and which one is not. So in this lecture, I'm going to talk about a lot of um, discrete random variable and their mass probability mass distribution and function. So you can already see a list of those models: Laplace model, Bernoulli model, binomial model, geometric model, negative binomial distribution, hypergeometric distribution, and finally the Poisson distribution. So I think in this class I will only talk about the first six and the Poisson distribution, which is I think it's more advanced and harder to understand, which I will put in the next lecture to explain how their mass function are derived and what their application is. But for the first six, the main reason I think the most important thing to know about is how their mass probability function is derived from the formula we already have and by our logical operations. That's the main thing, and also how it can be applied to realistic events. For example, maybe you have heard the famous um, like the gambler's ruin in the last lecture, what their model is. But unfortunately, I don't think it belongs to any of those, but they're composed of the Bernoulli distribution. So I think those are the focus of this lecture. And first of all, the the easiest one is the Laplace distribution, because the Laplace distribution is the same as Laplace experiments, which we have already explained in the first week. So in the Laplace distribution, the sample space is pretty simple. It's from 1 to n. It's a list of the positive integers. And their mass function is defined as clearly as it was. Like if for all of the integers in the set in the sample space, the probability that it happens is 1 over n. It's 1 over the sample size, which is, say, each of these positive integers have the same probability to be found or to occur naturally. So this is the mass function, which is pretty simple. And however, I would also like to stress that if we say like the k here, k is not in the set, then the probability that k occurs is 0, because we don't have a probability that nothing exists in the sample space can happen in Laplace experiment. So let's have an example like the X, which is the sample space. Let's say it's the outcome of a rolling die. It's rolling a six-sided fair die. So all of the side with the number occurs 1 to 6 is 1 over 6. So when the number so if we say, well, 3.4 is a number with a decimal, it's between 1 and 6, so it's in the set, but it's not, because it's not integer, and 3.4 is not occurring in the set, so the probability is definitely 0. And for the second Bernoulli distribution, I would say it's simpler. It's simpler than a Laplace distribution. Not because they have probability already occurs, like they have one parameter, but it just have two cases. So the set becomes less, because in the whole sample space, there's only two probability, whether it's a success or it's a failure, and we define the probability that a success occur is p, is the probability parameter we want to find out, or we already know. So this is an abstract version of a coin toss, because the coin toss have imagine it's an unfair coin, so the success probability is not always 1 over 2. So yes, it has some probability to fail, but some probability to success. But if we add them together, there's only two choices. So the overall probability is 1, which is satisfy the total law of probability. And the distribution, we define it as the X on the sample space will only contain 2 elements, success and failure. And we define the outcome. If the outcome is success, the X, the random variable, random variable send us to 1. And if the outcome is failure, then the random variable send it to 0. So this is how we define a Bernoulli model. And the math function is pretty simple, like because there's only 2 outcomes that might happen, 1 and 0 in the random variable version, so we can write them out. So the probability that 1 happens is P, and probability that 0 happens is 1 minus P, and sum them together is 1. So that is the model of the Bernoulli distribution. And just consider that if for example, like the X, the Bernoulli distribution P is 1/2, then this denotes the success of 1 occurs is P, and the is P, which is 1/2, and the probability that 0 occurs is also 1/2. But for this one, the success probability is 3/4, but the 0 probability, the 0 occurs is 1/4. So it's slightly different. And we always for these discrete models, we usually use X as our random variable, right hand first. Then with this kind of a zigzag pattern, a zigzag line with what the model is, the name of the model followed by that, and with 3/4, which is the parameter. So in the Bernoulli distribution, it only has 1 parameter, but we can see that in the later, more complex distribution, it can have different parameters. And so let's have a logical training here. So what is the Bernoulli random variable? If they are random variables, or if they're not random variables. So I think this is always a good question to ask yourself when you are meet with a new formula, because we already shown, like last lecture, where we already studied like how to prove what's the characteristic of a probability space, like what function is a random variable. First, it should be measurable, and this is the condition for a measurable function. And so if that's measurable and it turns out a sample space to the real line, the real number line, then we can say it's a random variable. So in this case, we have to prove that the function, the Bernoulli function, this one is it's measurable. If we can prove it's measurable, and we can say the outcome is already the 1 and 0, which is in the real number line. There's only 2 points, so we can prove it's a Bernoulli distribution. If we fail to prove that, we have to find a new formula, because that is not a random variable formula. So let's first begin with, we know that X Bernoulli P is a measurable function. So how we can prove this statement? How we can prove this statement? So first of all, we want to find out all of the outcomes smaller or equal to a number is always in the power set of its sample space. So first of all, we have to find out what is the power set of the sample space. Sample space contains S and F. So the power set contains S, F, the empty set, and overall the full set of the sample space, which we have already proved at the beginning. And then here we select for the alpha, which is a random number, we can put into 3 cases, because we know that if S happens is 1, if F happen is 0. So the first case is if the alpha is in the range of 1 to infinity, which means it's greater or equal to 1. So in this case, we can say if it's greater than 1, so absolutely the overall sample space will happen. And by the same time, the S set will also happen, because that is also like greater. So both F and S will happen. So in this case, it's we'll say the overall sample space would happen, and this is in the power set of the sample space. So we prove that if the alpha is greater or equal to 1, the function is measurable. And the second case is another portion of the real line is greater or equal to 0 but smaller than 1. So in this case, we can say we can find out the value, the xf, the f is contained, but S is not contained, because 0 is contained in the set, but 1 is not. So the only case that all of the outcome can only be F, because S is missing here. So as a result, we can say, is F in the power set? Yeah, it is. It's here. So F is satisfied with this condition. So we are only back to one more portion of the real line, that is from negative infinity to 0. And in this case, nothing's happened, because both F and S is not in this range. So only the empty set will take the place. So all of the is like 0 probability that the outcome will come from this range. So it's empty set, and empty set is also in the power set. Okay, so we prove that for all the alpha in as a real number, it is satisfied as a measurable function. So we prove this formula is definitely a random variable function. Yeah, so let's check for some real situation thing, if some cases are Bernoulli random variable or not. Rolling a die 100 times and observe whether getting even or odd spots. It is, because it's only have 2 outcomes, even and odd, and if we sum them together, the probability is 1, so it's satisfied. Or observe the daily temperature, see whether it's above or below freezing temperature. It is, because it is a Bernoulli random variable. Above is the success, or below is the failure, and there's nothing in between. So it is Bernoulli. But the third case is like the sample 1,000 people and observe whether they belong to upper, middle, or low social economic status. This is not, because they're classified into 3 cases: upper, middle, and low. But in all of the Bernoulli random variables, we can only treat them as 2 categories. So it fails to be a Bernoulli random variable. But we combine the upper and middle into 1 category, it is satisfied. And the third model we're going to explore today is the binomial distribution. Binomial distribution is, you can view it as a sum of the Bernoulli distribution. So always thinking of the model is to say, well, we have blue ball and the red ball inside, like that. The blue ball means success, so the probability that draws a blue ball out each time is p, and draw a red ball, which is a failure, is 1 minus p. And we'll count how many of the blue balls will occur finally. So this is our old way of thinking, if you only know the experiment before. But now we have random variables, so we can say use the binomial model. We'll only consider about draw n independent Bernoulli random variables out, because each of the drawing can be treated as a Bernoulli distribution, whether it's blue or red, and count the success. So how many of the Bernoulli random variables are 1, and that will find out the p. That will find out the p times n, which is the number of blue balls as the old way of thinking. So let's introduce the binomial distribution. The binomial distribution is a sum of all of the Bernoulli distribution, because each one, like in the ER model, in the previous page, if we sum them all up, it goes to 1. It goes to like the all cases. So it can be separated into Bernoulli variables, and the formula for the binomial distribution is this one. It's pretty long, but how it formulates is very reasonable. First of all, let's say there are two parameters here, n and p, and n is the total number of you can say the balls you are selected from the urn, and p is the probability that the success color of the ball will occur. So the p to the power of k means the number of the success ball that come out, and 1 minus p times n minus k is the n minus k number of the unsuccessful ball that come out, the failure ball come out. And so that means you're already satisfied with exactly you select k balls out. But why we need the combination of n to the k? Because that is, you imagine that all the balls are in a line. They are like red, blue, blue, red, red. If you are selecting n equal 5 and the success rate is 0.4, so there are only 2 blue balls, but there are other probability, like the blue ball can be the first, like blue, red, red, blue, red, something like that. So we'll need to compute a combination of those cases happening together. So that turns out to be a combination of n to the k. So this is how we calculate in certain cases if we want k success cases to occur in the total n cases. So we denote this distribution by binomial Pn. Well, let's see an example of that. So the famous Mendelian theory, which is like an introduction to genetics in biology, across fertilization of the related species of red and white flower plants, they produces an offspring with 25%, which is 1/4 red flower plants. So now we are across 5 pairs of flowers. So in each of the cross fertilization, the success rate for a red flower is 1/4, and the failure rate is automatically 3/4. So but there are we cross 5 pair of flowers, so there's like, which means the n here is equal to 5. There are 5 independent Bernoulli distribution. So we can denote this model as x binomial 5 1/4, which is the n and p. So let's calculate that out. The probability that x is equal to 0, because we'll calculate that no red flower occurs. So the flower is equal to 0. The red flower is equal to 0. So that's 5/0 times p to the power of 0 times 1 minus p to the power of 5 minus 0, which is the n minus k, and is 5k0. And this term remains, is 1 minus p to the power of 5. This term goes to 1, and this term also goes to 1. So like 5 factorial divided by 5 factorial times 0 factorial. So it's 1. So it goes to be 3/4 to the power of 5, which turns out to be 0.237, which is not very low. That is because the original probability, 25% for red flowers, is already low. So there's still some probability that the straight 5 flowers are all non-red. And another case is to calculate at least 3 flowers are red. At least 3 flowers red means, which means that we cannot have the case of 5 and 4. So it's like the total probability, which means if we add from k equal to 0 to k equal to 5, it will be around it will be exactly 1. So if we use 1 minus the p the k equals to 4 and 5, we'll get the probability that at least 3 at most 3 red flowers. That's at most. So we'll ignore 5, 4, and 5, and that's always a clever strategy when we say at most, at least. If the other side is smaller, so we'll find out that we'll calculate the smaller version first, rather than the larger version, which will bring us a lot of computation. So in this case, we use px smaller equal to 3, and we calculate as 1 minus p equal to 4 and minus px equal to 5, which turned out to be 0.984, which is really close to 1 in this case. So which means red flowers occurs at all flowers or 4 flowers is pretty low. And the fourth model is the geometric distribution. So this one is also like a sum up of the independent Bernoulli distribution, because we can say what this means is we would like to define the variable x for the waiting times until the first success occurs. So this means the k we want to find out is how many is the which step we take is the first success occur, which means the previous cases are all failure in this case. So we define the discrete random variable x as a geometric distribution with parameter p. We only have one parameter here, which is very lucky. So the probability mass function is it's 1 minus p to the power of k minus 1 times p, for k equal to 1 to something to infinity. Okay, so this can be denoted by geometric p, because the probability that a success happen is the only parameter here. So why is true? So you can pause and think for a little bit. It's very similar to the binomial distribution, because 1 minus p is the probability that failure takes. So if we find out the first success is occurred at the k, which means the first k minus 1 cases are all failure. So we need to time them together. And the final one, the k position is a p, so there's only 1 p. And we time together as because they're all independent, we time them together and we find out that's the probability. Because so why in this case we don't need a combination as in the binomial distribution? Because the binomial distribution, we can have like success, failure, success, and change as success, success, failure. But in this case, if we change any of the failure before, it doesn't change, and it's only fixed out like it's the failure, 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 success is in a straight row, and we are not able to change that. So there's only one possibility of the permutation or combination. I think it's combination of these results happens. And yeah, so we're going to find out whether the geometric distribution is a random variable, or if it's a probability. Okay, so let's try out. So first we need to prove if that's a probability mass function, all of the terms should at least be non-negative. So we can see here, because p1 minus p is greater or equal than 0, and p is greater or equal than 0, and a non-negative term times no matter what real number is non-negative. So a non-negative times non-negative is still non-negative. So all of the terms are non-negative. And also want to prove if the sum up of all of these cases, k from 0 to infinity, if that equals to 1, because the probability mass function always sum up to be 1. So we can sum that to try if that's 1. And we can say k from 0 to infinity is p times 1 minus p k minus 1, which is a formula. And because p doesn't have the term k, so we can extract it out to calculate this first. And we can say this is a geometric series. This is geometric series. So we can use the sum of the geometric series to simplify that, which is first term 1 and 1 minus the ratio, or 1 minus p. And we find out that this is p. It's p times 1 over p, so it's 1. So that is satisfied too. And there's a new problem called compute the probability that t is greater than k. So what is that? So intuitively we say, if we don't want to compute in a very complex way, we need to think cleverly. What is t greater than k? Which means the first success is happening at least k plus 1, which means this is the same. The complementary set is saying, okay, the first k must be failure. So we just need to calculate the probability that first k steps are failures, which is 1 minus p to the power of k, which is the final answer here. But if you want to calculate all of the cases to sum up all of the j from k plus 1 to infinity, to sum them up, the result will be the same. So there's two ways to handle that, and I prefer the intuitive thinking instead of the rigorous proving in these simple cases. And for the geometric random variables, there's for the geometric distribution, there's one more property called the memoryless property, which is also called the Markov property in the Markov process. This is to say, if we want to show the t is greater than j, the probability t greater than j is the same as t greater than k plus j, given by t is already greater than k. That is to say, the probability that you move from 0 to 10 is equal to the probability that you move 90 to 100, because the 90 sounds like a k and the j is 10. Okay, and that is easy to understand, because imagine you are beginning at a 90, and at least the first success is 101, so you are moving 11 steps. But if you are 0 and the first success is at least 11, you're also moving 11 steps, so that's the same. And if you can prove that by saying using the conditional probability, using this formula to find out, and because t greater than k plus j and t greater than j, this is given only by leading by this term, because t greater than j is contained in t greater than k plus j. So, but the lower part is also t greater than j, t greater than k, and we will simplify the p term out, and only remains 1 minus p to the power of k plus j and 1 minus p to the power of k. And we divide them to find out it's 1 minus p to the power of j, and which is the same as t greater than j. And we are done our proving. And our next model is the negative binomial distribution. Oh man, this is very similar to binomial distribution, just negative. Why? Because so how this model works is we would like to define a random variable x, which counts the number of failures before the first R success. So which means that is the probability that how many failure will occur. The K denotes the number of failures, and we already know the last turn is a success. The last turn in the sequence is a success because those failures are before the R success. So the endpoint is success. That's we already know. So given by that information, we can easily write it out because the number of R, the number of success is R. So in this case, P happens R times, and the K happens 1 minus P, and the 1 minus P, which is the failure, happens K times. So we time them together to get a sequence of failure and success. But we do not use the combination as R plus K to the K. That is misleading because the last term is already defined as R. So we don't want any K to happen in the last position. So only the R plus K, or we can say the N, the total number of success and failure, only the first and minus 1 cases can move, and the last case is fixed. So it's better to say is R plus K minus 1 to K combination. And we denote this distribution with 2 parameters R and P by MB, RP, because MB means the negative binomial. I think in this case, this model is very efficient in some like sports game. Yeah, I watched the NBA playoff before, and the rule is that if a team gets to the 4th success, the team will pass to the next round. So we always want to calculate how many failure, what's the probability, like 1 failure, 0 failure, 2 failure, 3 failure occurs before the other team is success, which means already hits the 4. So that's very interesting to find out. So like the business person will always find out that to find out like how many number of game is possible. So they'll always like put the advertisement into those games these are the last game to make the most benefit. So that is how it applicates into the sports field. I think like the NFL and the NHL, they are all playing with the same in the playoff season. So that's the application of this model. So we are moving to the last kind of model for today, which is the hypergeometric distribution. Okay, so this is I think this is very also related to binomial distribution, but from another aspect, because for the binomial distribution, we already know the exact P, which is the probability that success occur. But in this case, we do not know the population P or the exact number of P, but we know another thing, which is called the reservoir. We have the large population, the reservoir, given by N, and we know that the M are defective and N minus M are non-defective, which is good. So in this case, we treat defective as success and good as failure. This is I think this model is applied to most of the the warehouse workers or storage management, because they'll find out like they get a sample from the storage and to find out how many of them are damaged or defective to conjecture what's the portion of the goods is already damaged in the warehouse. So that is that is useful aspect of the hypergeometric distribution. Also in biological spaces, like the researchers want to find out a group of animals, like what's the number of the want to find out what's the number of animals inside that the population of animals. So they will not do the they will not catch every animals, but they will catch a small sample, detect them, and to put it back to find out like what's the portion between them. So this is still very useful. And the old way of thinking, when we learn the R models, we think of like the urn with m blue balls and n minus m red balls, and we draw m balls out and find the number of blue balls, which is very similar to binomial distribution. But the new way of thinking is we'll have a hypergeometric random variable with parameters n, m, and small n, which is the sample size. And we'll illustrate this new model in the next page. So the discrete random variable x is a hypergeometric distribution with the parameter n, m, and n. If the probability mass function is given by the combination of m to x, the combination of n minus m to the n minus x, divided by a combination of n larger n, capital N to small n. And but one specialty of this model is that the x here is given by the range, not from 0 to n, but it is from the maximum value between 0 and n minus n plus m to the minimum value between n small n and capital M. This is because x definitely it should be smaller or equal to n, because that's the that's the sample size, but it also need to be smaller than the total number of like the defective goods, the defective items in population. So if n is greater than n, we cannot have n. We can at most have m, right? So the same logic can be applied to the lower bounds, because of course x is greater than 0. That's right. But if the total number of the sample minus the good thing is greater than 0, so it will at least contain some of the defective items, because the sample size is already greater than all of the good items. So if you draw n sample out, at least some of them will be the defective one, and that's m minus the number of good items inside. And as I said, that the hypergeometric distribution is very similar to a binomial, because as n goes to infinity, like our reservoir population goes to infinity, which limits the probability, the ratio of m divided by n as closer and closer to the exact p, and if that happens, if that's go to the real infinity, and that's become a binomial distribution. So and in that case, we treat the three parameters n, m, and n as the n, which is p times n, and n is still n. So the p and n comes in, p and the small n comes in as our binomial distribution, and the n goes to infinity, so we don't consider that anymore. And we'll see one more example of the hypergeometric random variables. So let's say there are n deer in a region. We capture 5 of them and tag them, which just means 5 of them can be discerned out, so and put them back. And we always capture back like 10 newly captured deer, and that's another way. So in the first study we capture 5 deer. In the second study we capture 10 deer, 10 new deer. So and X of them are tagged. We find out that's the result of the second study. So that's usually a useful cases in the hypergeometric random variable, because we don't know the population. We only know we tag 5 of them, but we can use the ratio of 10 divided by x to find out what's the population, what's real population divided by 5. The ratio should be similar in the hypergeometric cases. So let's assume that the population of O we already know is 25, and find out the probability that X is equal to 2. So in the hypergeometric distribution model, here N is 25, M is the defective term, in here is the tag there, which is 5, and N is 10. And X here is 2 because we assume that the X is 2. So find out the probability that X equals 2 becomes by directly plugging this formula here, and we can find out the result is about 0.385, which is pretty high, because we only consider one case and it's nearly half of it. That is because the ratio we are counting is exactly the same. Imagining like 5 divided by 25 is 1/5, and 2 divided by 10 is also 1/5. So this is the largest possible cases given by all of the single X come out. And and I think that's mostly about today. And for the next lecture, which I think I'll held next Monday, we'll talk about the Poisson distribution. And that distribution is more useful in like anticipating something will take place or will not take place in a certain time slot.